Okay, so we talked about volume fraction. Fundamentally, volume fraction is relevant to mass conservation. It's a quantity that tells us the ratio of volume or the ratio of mass. So this is relevant to mass conservation. We've defined it already. We're not going to go through that again. It is going to be highly relevant for the question of whether we have a dilute or a dense flow. So we're going to talk about that a bit in the next few minutes. So it's going to help us differentiate between dilute or dense. Then a very important piece of your desk. We can think of an equivalent, or not equivalent, but another quantity that's going to be not relevant to mass conservation, but relevant to momentum conservation, or to momentum exchange between the phases. And that's going to be what we're going to call mass loading, or mass fraction, if you will. So there's many ways. First of all, I'll make it clear that there's many definitions, many different quantities that people look at. But that's going to be relevant to momentum. So instead of looking at the ratio of volume, we're now going to go one step beyond and look at the ratio. Well, a couple of ways you can think about it. You can look at the ratio of mass in the system, or you can look at the ratio of momentum in the system. So I'll give you a few examples. What's probably used the most often is the ratio of the mass in the dispersed phase to the mass of the mixture. People look also at more direct mass ratio, and we'll make use of that as well. So if I just look, let's call it C, just the ratio between the mass of particle to the mass of fluid. So that's going to give me, I can write this as rho. I think we've been using D times alpha D over rho of the carrier times alpha carrier. If you have significant slip between the phases, that means that if one phase is moving at a significantly different speed as the other phase, it makes a lot of sense to think about another quantity that would be a ratio of mass flow rate of both phases. So you would include now velocity. So you would have a rho d alpha d times representative velocity of your dispersed phase over rho c alpha c times uc. Well, this would be some sort of a reference velocity of the dispersed phase, or reference velocity, and here reference velocity of the carrier phase. So we'll talk about that. It's going to be important for us to, so this here, volume fraction, we said this helps us differentiate between dilute or dense flows. Mass loading is going to help us differentiate between coupled and uncoupled flows. So basically we're going to say that no matter whether the flow is dilute or dense, if the mass loading is high, then dynamically the particles are going to be important to the fluid dynamics. And the converse is true as well, no matter whether the flow is dense or dilute. If the mass loading is low, if the particle mass is negligible, then the momentum equations for the fluid will essentially not care about the particle phase. So that's going to help us It's going to help us differentiate between coupled and uncoupled flows. I'm going to talk briefly, so we're kind of going through more of a bit of a laundry list of important concepts regarding a dispersed ensemble of particles in a flow. An important concept that we've not talked about so far is the question of how the particles are distributed locally. We've talked about this characterization of the volume fraction or the number density, but there's an infinite number of ways that you can arrange particles that will lead you to the same local volume fraction. And that can be very important. And the importance of that, in fact, will show up in a number of situations. So if you compute number density, which is not a first order but a zeroth order statistic, can consider, say, a 15% volume fraction flow. So a flow where I have 50% of my volume occupied by particles. Depending on the physics, that could look very different. You could imagine a uniform distribution of those particles. Or you could imagine a system like this. The point I'm making here is that we're going to have to start worrying very much about high-order statistics of our distribution. We're going to have to start thinking about variance of our distribution function in order to differentiate between those two cases. So this is the same alpha d, but different distribution. And in fact, something like that is completely expected. In fact, I would argue that we're getting more maybe into chemical engineering, but there's a very important chart there called the Geldart Chart. Or the so-called Geldart Classification, that looks at the different properties of particles and tells you whether they're expected to behave as completely independent grains, essentially, or if they're expected to behave more like a powder that will stick in various ways. So if you're interested in moving particles around, and if you're a chemical engineer, typically the first thing you'll do is you'll go to your Geldart classification, plug in the parameters for your particles, and figure out whether the particles are going to stick to one another like a very fine powder. And this is what we would call then a Geldart type A particle. It might be, for example, instant soup. That might behave like this. And then in that case, good luck flowing it. Good luck having it conveyed and manipulated It's going to be tricky. It's going to require a lot of care. Those particles will stick. Or you can be looking at Geldart type B, like grains of sand, are going to behave essentially very nicely. They're not going to stick on one another. They're going to live they're going to be pretty easy to deal with. So we'll go back to that in a second. In fact, I don't know why I didn't include that right here, but at the bottom of the next page, we'll talk about the importance of looking at the variance, as well as other parameters that are able to differentiate this. So this is going to also lead us to the question of clustering. So we're going to start becoming more and more interested about whether the particles are exhibiting this tendency to gather in certain regions and become depleted from other regions. There's going to be reasons why this might happen, and we'll talk about that today. A quick point that's going to be useful for us to discuss as we move forward is this simple, very naive question of how. So if you were asked to distribute particles, say to initialize a simulation, maybe the simplest thing you would think of doing is to just arrange them in a lattice. So just draw a little grid, and at each intersection you would place a particle. This simple arrangement is pretty practical because it allows us to think about, simply at least, think about interparticle distance. So we'll talk a bit about that for a second. If I give myself a nice little lattice arrangement, okay, something like this. Oop, that's too big. If the characteristic size of that lattice is L, and my particle diameter is D, then I can trivially compute my volume fraction. In 3D, which means that I can compute L over D easily as well as such. So this is a made-up thing. It doesn't typically happen in nature. It's something that might be practical for an initial condition in a simulation. The interesting thing is that it gives us already this, this connection between the interparticle distance and the volume fraction. We don't need to assume a lattice to have this connection, but that makes it completely obvious. So if you have a certain volume fraction, there is going to be a corresponding expected interparticle distance. And that interparticle distance will start playing a very big role when you start asking yourself whether you should worry about collisions or not. So I'll make a couple of comments. So first of all, one comment is that, again, this is a made-up arrangement, and really, I should say this is not the only lattice. That's pretty obvious. This is what you would call a primitive cubic lattice. You could imagine a cubic face-centered lattice. You could put particles on the faces. There's lots of other things you could do. We're not going to worry about this. It's just one made-up configuration. But it allows us to start thinking about, so what is a small enough alpha D in order to neglect collisions. And here I'm talking about not collisions with walls, but collisions between particles. So it gives us a first opportunity to think about this. Obviously, you have to make a choice. One might argue, well, if the interparticle distance is significantly larger than the particle diameter, it would be reasonable to assume that we don't have a high likelihood of collisions. Where engineers will say that significantly larger means an order of magnitude. So let us say maybe an L over D on the order of 10 might be a reasonable estimate. If you do this, that will give you, from what we've done just above, an alpha D on the order of 10 to minus 3. So what we're saying here is that going back to this idea that volume fraction will naturally allow us to distinguish between a dilute and a dense suspension. Well, this is essentially this argument here, that a dense suspension will be a suspension where the number of particles, local concentration particles, is high enough that one would expect collisions to matter. A dilute suspension will be a suspension wherein the interparticle distance is high enough that we can expect collisions will not happen. And so here we're saying 10 to minus 3 is a reasonable place to make this, this differentiation. If we go back to the question of mass loading, so if I just think about the mass ratio, the mass in the particle phase and that situation over the mass in the fluid phase. Well, let's say I consider water droplets, okay? Let's say this is water droplets in air. My density ratio is on the order of 1,000. If my volume fraction is on the order of 10 to minus 3, then my carrier phase volume fraction is essentially 1. And therefore, my mass ratio will be the density ratio times alpha D. We said our density ratio is 1,000. And therefore, my mass ratio is 1. So let me write this down a bit. I think we wrote that as C in the previous page. So in this case, C would end up being rho of the drop over rho of the carrier times alpha of the drop over alpha of the carrier, which is approximately rho D over rho C times alpha D, which therefore would be approximately 1. Okay, 10 to the 3 times 10 to the minus 3. So the point we're making here is that the distinction between the dilute and dense flow, as in the distinction between a suspension wherein collisions might be expected to a situation wherein collisions might be not expected, will be very different from the question of where the mass is. So basically we're saying even though the flow might be dilute, so below 10 to minus 3, the mass in the particle phase might still be very far from being negligible. So the hierarchy is then going to be this. We would expect that at very low concentrations, the collisions are going to be unlikely and the fluid phase is not going to be influenced. It's going to be negligible as far as the particles are going to be negligible as far as the fluid phase is concerned. As we crank up the volume fraction, we're going to get a region where the particle collisions can still be neglected, but there's going to be two-way coupling. Basically, the fluid phase will be responding to the presence of the particles because the mass loading will no longer be negligible. And as we keep increasing the volume fraction, we're going to have a situation wherein, yes, the fluid is influenced, but also the particles are going to be influencing one another. Okay? Classically, we'll go back to that. We'll put that in a little table. But classically, this is what's called one-way coupled is the very left side, the far left side of this, so low volume fraction, fluid not influenced, no collisions. This is what's called one-way coupled. Two-way coupled is where the fluid is influenced, but there's still no collisions. And classically, people have referred to the situation where the particles are also colliding as four-way coupled. Okay? So we've done that with the lattice. We don't need to do that with the lattice. We can make a distribution random within our within the local volume. And that's what takes us to what's called the Poisson distribution. If I randomly place particles at a certain, if I randomly place n particles in a certain volume, then I will get the so-called Poisson distribution. Well, that doesn't look very random. So the Poisson distribution is then the statistical process with uniform but random particle placements. This is what we did at the inflow in our toy code 2 days ago. At the entrance, we picked a position, a random position, and we placed a particle there. This is what's called the Poisson process. And so from that, you can compute again the number density, and you can do that analytically. We wrote something in 3D above. We'll do it in 2D here. In 2D, you can show that the interparticle spacing, which will now need to be some sort of a mean interparticle spacing, because it's going to vary from particle pairs to particle pairs, is going to be 1 over 2 times the square root of n, where n here is the number density chosen. There's one little subtlety that I cover next, but I think we can skip. I want to get to other things. If you use a simple Poisson process to distribute your particles, if you're looking at an aerosol, there's many situations where, provided the volume fraction is low enough, everything's going to be fine. If your volume fraction is becoming larger, that can become very problematic, because there's nothing in the Poisson process that prevents particles from overlapping. So that can be an issue. Why does it matter? Well, as modelers, if you place Lagrangian particles in your calculation and they overlap at the initial time and you treat collisions, those collisions will probably explode at your first time step. So it matters. So you'll have to be careful about this. There's different processes statistical processes that allow you to deal with that. I give one example of the so-called Mattern point process, but I'll let you read up on that if you're interested. Again, kind of the summary here is that we're going to need to worry about high-order statistics for our volume fraction distribution. An obvious one is going to be the variance. Well, let me say variance of number density. So if my mean number density is just the integral over my volume, this is not an array, of n dx. Then we'll be interested in the variance obtained from simply n squared minus n squared. There's another concept that I'll just touch upon briefly, the so-called radial distribution function. The radial distribution function is another way to think about the local characteristics of the distribution of particles. Variance is a one-point process. It's something you look at locally, and it's just how. Sorry, go ahead.
Should it be average by something, or is it just over the dx? We are integrating over the volume.
So yeah, here I'm thinking about integrating over a volume of interest, basically. So if you have a region of space at each location, you know what the number density is. You can gather over a larger region what the volume, the mean number density is, and you can also figure out then what is the variation in that number density over your space. Makes sense? So this is what we call one-point statistics. For those of you doing turbulence or having had some exposure to turbulence, we're doing high-order statistics, but single-point statistics. We're looking at a piece of information at one place in space. It is classical to look at more complex statistics, in particular two-point statistics, wherein we look simultaneously at 2 points in space. What's classically done in terms of two-point statistics, so here I'm talking about correlations, basically in turbulence, right? Well, the classical way that people have thought about analyzing the correlations between, in terms of particle position, is in terms of this radial distribution function. It is classically written G sub r, G of r, and what G is the number of particle pairs separated by a distance r. So you can see in what sense it is a two-point statistic. We're not looking at whether we have a particle or not. We're saying, given the fact that I have a particle here, how likely is it that I have another particle at distance r from that? Okay, and then you can average that. So basically, you're going to be looking at the distribution of inter-particle pair distances. So that's going to be the number of particle pairs separated by a distance r. So those type of tools then are brought to bear to analyze non-uniformity of the particle distribution. Where does this non-uniformity particle distribution come from? Is a reasonable question for us. So we're gonna, for I think the rest of the morning, we're gonna talk about that. So we're gonna talk about mechanisms leading to clustering. That's going to be the next couple of pages. Then I was returning to phase change, but I think we'll just skip that, and then I'll summarize with regimes of two-phase flows. So we're not going to spend too much time on this first part here. In those notes, what I was doing is I was going back to summarizing the single particle equations to help us move forward. But you know, we've done that. We know what those equations are. So we're going to have a dVdt is equal to a correction factor f as a function of Reynolds number for the particle over tau p times the velocity difference between the two phases plus potentially gravity. So we've talked about that already, and we wrote that a couple of days ago. So from that, what we learned is that the particle response time is found to be this. It's found to be this tau p here. That's a characteristic time scale that controls the coupling between the phases. And for this, and to this corresponds the equation that we wrote last time, f of a Reynolds number over tau p times the difference between the fluid velocity and the particle velocity. Okay, so this is going to be our equation. On Tuesday afternoon, we introduced the concept of the Stokes number. So here I'm defining it in a more official way because it's a critical parameter. If the fluid time scale is tau f, for example, we argued in our toy problem that this would correspond well to the shedding frequency of this, or I guess the inverse of the shedding frequency of our von Karman vortex street. Then the particle response time to the fluid, the ratio of the particle response time to the fluid response time would be the definition for the Stokes number. That's going to tell us the level of coupling between the fluid and particle dynamics. So first of all, so we did that already last time, but if the Stokes number is very small, then you can expect from that the particles are essentially going to be perfect tracers, and they'll follow well, let me just summarize this. I'll say as kind of a high-level description that the Stokes number characterizes the sluggishness of the particle response to changes in the flow. So if the Stokes is high, the particle responds very slowly to any change in the flow. The appropriate, so it's a slow response, the appropriate way to think about it would be to think of your particle as a cannonball. Doesn't care much about what the fluid is doing. It's too slow to really respond to changes in the fluid. So your particles will probably go through eddies and fluctuations without seeing much of them. If your Stokes number is low, it's the opposite situation. You have a near instantaneous response. So I'll just say rapid response, but in the limit of vanishing Stokes number, you have essentially an instantaneous response. Therefore, if ST goes to 0, you get into what's called tracer particles. Tracer particles are specifically used for PIV, for example. Right? If you want to do measurements on a fluid phase, typically you do that by tracking particles. If you want your particles to be a good surrogate for the concept of a fluid particle, you need those particles to be very light, very small, so that their velocity is essentially at all instants the velocity of the fluid. You can crunch some numbers. I'll give you one example. One point of one anchor point. If I take a water droplet in air, if I set its diameter to 100 micron, the corresponding tau p for this particle or for this droplet is going to be on the order of 30 milliseconds. Okay, so fine, we talked about that already. Now what's going to happen if the flow is turbulent? If the flow has a range of turbulent flow structures or a range of eddies that exists on a range of timescales? Well, things are going to be pretty interesting.
How do I estimate my accurate fluid time scale?
So that's exactly what I was going to talk about. So it is not a simple question in a general sense. I'll give you the classical, fairly well-accepted answer. It is not a sufficient answer. And I can point you to a couple of papers that have come out more recently that try to go a little bit beyond that. But we'll provide one answer to this, and you know, we'll see what it means. So if you have a turbulent flow field, or let me say turbulence. So I imagine most of you have been exposed in some way to turbulence. That will involve a range of time, velocity, and length scales. So the question becomes, what is the appropriate the appropriate time scale to use in a flow like this? The naive answer is, well, let's put particles in a turbulent flow field and look at the response in terms of the development of inhomogeneities and look at the particle trajectories. And let's see what time scale gives us a nice transition from a small Stokes to a high Stokes that seem to match with the changes in the behavior of the particles. That's kind of pragmatic. Basically, what is a time scale that seemed to tell us something of interest, and what is the time scale that makes the Stokes number the most relevant to the analysis of experiments? If you look at this from this perspective, then the answer is you should take the smallest time scale in the flow field. That is the Kolmogorov time scale. So if you consider the smallest eddy, the smallest turbulent eddy in itself is a kind of an interesting concept, but from an energetic standpoint, you can argue that it exists, it's a reasonable quantity, and it's referred to as a Kolmogorov scale, and it's classically written eta. So if you consider this an eddy of the size eta, below which there's no turbulence anymore. What you have is only a linear velocity field. Above which there's a range of larger eddies. What you can do with this is build the corresponding time scale for that eddy. And we're simply going to call that tau eta. Then, from a fairly pragmatic standpoint again, it's been found that the corresponding Stokes number seems to be pretty effective at characterizing changes in behavior of particles in turbulence. So that leads us to an ST eta definition, which is then tau p over tau eta. This is today still by far the most often used definition. And again, from a pragmatic standpoint, from experiment, it seems to be most relevant. In what sense? Well, in the sense that if you go from a Stokes eta well below 1 to a Stokes above 1, you see a complete difference in the behavior. Basically, if you distribute particles in turbulence, homogeneous isotropic turbulence, at a Stokes number of 0.1, essentially nothing of interest happens. The particles get mixed around, but there's no particular interesting physical phenomenon. At a Stokes number, say on the order of 10, same thing, not much happens. On the Stokes number on the order of 1, you start seeing a very different behavior in your particle distribution. So this is what I'm trying to illustrate with these images here, coming from John Eaton's group at Stanford. Pretty recently, this type of things has been really figured out and quantified only in the past 10 years. So that's what we call preferential concentration. Let me make a point here. So the essential point is the following. For ST eta on the order of 1, preferential concentration is observed. How do you do that experimentally? Well, you create you know, grid turbulence so that you have a region of homogeneous isotropic turbulence, and then you distribute different types of particles in there. And you can change their density, you can change their size. You can change them in a way that allows you ultimately to have a different effective particle response time, since the particle density is what shows up in the numerator of the tau p calculation. And this is what you see. So I think it's written down there in the, yeah. So, yeah, the values are here. So those three images come from, so here they wrote STK for cosmograph. This is a value of Stokes number of 0.5. This is a value of 1.3, and this is a value of 8. What should be maybe not completely obvious, but I think reasonably visible, is that in that situation here, you have an ST eta of approximately 8. The result is essentially a uniform distribution. There's nothing particularly striking about the distribution of particles. Once you go around 1, though, there's something very, very clearly striking. And I'll highlight it here, that there's regions where we have way more particles. Right? Those regions have way more particles. And similarly, there's regions that are essentially devoid of particles. You have this big blob here that seems to see essentially no particles. We don't see much here. We see almost nothing up here. This region is devoid as well. There's an entire empty space here as well. So this is what we refer to, so this is ST, oops. ST eta is equal to 1.3. And there we see a tendency from particles to concentrate preferentially in certain regions of the flow and leave preferentially other regions of the flow. Once we go down to an ST eta of 0.5, I think, 0.6, it's close enough to 1 that we still see some remnants of this. And if I were to add another picture at the lowest Stokes number, it would be completely gone. There's a region that's more densely populated here, and there's still empty regions as well. So this definitely, this lower Stokes number also definitely shows preferential concentration. So, what's going on there? Well, we'll talk a bit about that as well this afternoon when we start talking about Eulean methods. But, and in particular, we'll derive exactly how you can obtain a quantitative version of what I'm going to say. But essentially, this is what happens. Imagine, so turbulence is a collection of eddies. An eddy is a vortical structure of some sort of coherence. So imagine a situation like this. We have here one eddy on the left, one eddy on the right. This is a turbulent eddy. This is eddy 1. This is eddy 2. Two counter-rotating vortical structures. Okay, turbulence is what it's all about, a collection of those things. Now imagine I place a particle in that. I place a particle right here at a given time. The question is, what is going to happen to it? Well, the answer to the question what will happen to it is a function of the Stokes number of that particle. So we'll consider three cases: infinitesimal Stokes number, a large Stokes number, and the Stokes number on the order of unity. So if I have first an infinitesimal Stokes number, we argued already that the consequence should be that the particle should be essentially a tracer. So if my Stokes number is very low, I would expect my particle to follow my fluid streamline perfectly. If now, I don't know if this is very readable, let me rewrite that. So this is St eta much less than 1. Now, if I have a large Stokes number, that particle, we argued, should behave like a cannonball. So we would expect it to just live its life independently of what's really going on with the surrounding eddies. So if my St eta is much larger than 1, I would expect this to happen. Well, in both extreme cases, we would expect, at least naively at first, we would think that if the particle follows the fluid streamlines, then it will not lead to non-uniform distribution because the fluid itself is divergence-free. Okay? There's no dilatation that takes place in the fluid phase itself because it's, at least at low Mach number, it's going to be incompressible. So particles following the fluid streamline should not preferentially concentrate. Now, this cannonball behavior, we don't know anything really a priori. There could be more things happening. And in fact, we do observe high Stokes number clustering as well. And we'll talk more about what that can mean. But here, basically, we're saying that there should be no specific thing happening at high Stokes number. The particles don't care about the turbulence. The interesting thing is going to be what happens if you find an appropriate intermediate Stokes number such that you get ejected from that vortex, but cannot get into the second vortex. Well, you find that this happens at a Stokes number of about 1. Where the consequence will be particles getting ejected from vertical regions in the flow, but not having enough inertia to penetrate other vertical regions. And so what we'll see is that the vertical regions, basically the little vortices, will be spitting out particles out of themselves, and all the particles will end up accumulating at the interface between those vortices, basically regions of high shear. We'll show in the Eulerian framework that you can actually write that fully. You can derive equations that will show you as a source term of particle number density the local amount of shear, and as a sink term the local amount of rotation. So we'll actually derive that. It's not something that is made up. This mechanism is referred to as the Maxey and Rayleigh mechanism. For preferential concentration. And it fits really well with the description that we've had based on the Kolmogorov time scale for the fluid. There are a lot of questions you should ask yourself. If I have a particle that has a high Stokes number when it's based on the Kolmogorov time scale, does it mean that it will also have a high Stokes number if I look at larger time scale in my fluid, right? If by definition, my turbulent flow will have multiple time scales, some small time scales, but also some larger time scales. So it is completely possible for this mechanism to not seem to be relevant at the Kolmogorov scale, but become relevant at larger time scales. So that goes back to the question that you were asking. It is not obvious that the proper time scale is the smallest turbulent time scale in the flow. It could be that your Stokes number based on Kolmogorov is larger than 1, but your Stokes number based on larger eddies is 1, in which case you would still expect to see preferential concentration. And so then the question becomes, what is the appropriate time scale? Well, really the question is there energy in your flow at a time scale that can resonate with your particle response time? So if you know what your particle response time is, then the question that you should ask yourself is whether your flow has any type of physics, of dynamics on that time scale, in which case you should expect some resonance to take place in the form of this preferential concentration. Oh, I'm already running out of time. So let me just add, let me see what I missed here.
And that way you should looking some kind of eddy spectrum of the fluid.
Yes. Yes, you should. And again, I can point you to a paper. There's a recent paper coming out of Lance Collins' group. It's from Cornell, and it's independent of, but basically I'm aware of this very nice study. It's a JFM that essentially proves that. It essentially goes through the same analysis of preferential concentration, but instead of just assuming that everything can be done at the smaller scale, it just looks at whether we can argue that this should happen on a resonance time scale that is on par with the particle time scale. So it's a 2012 or 13, or maybe even 14 JFM by Collins and his postdoc, and I don't remember his name, but I can look it up and give that to you. That gives you a more comprehensive understanding of this. Okay, let me add quickly a few things, and then I'll let you go. Clustering goes well beyond preferential concentration. Inhomogeneity can arise for other reasons. So we'll talk not tomorrow, maybe tomorrow, I'm not sure. No, maybe the day after tomorrow. We'll talk about clustering arising just due to flow instabilities. This is an example of that. I think I showed you a video of that on the very first day. If you let particles fall in the vertical tube, you'll start seeing the formation of clusters, denser regions. And this is something that will happen and be fairly predominant in fluidized bed reactors and fluidized bed risers. So this is an example of clustering. So non-uniformity developing of particles in a vertical flow. Vertical matters, we'll talk a bit about the criteria for this instability to develop. So we'll isolate that a bit. So this is clustering inherently due to an instability. What you need for that is a non-negligible mass loading and some mechanism sustaining slip. Basically, gravity helps for this. So if you have a vertical flow like this, gravity will pull the particles in one direction. You can flow in the other direction. That will lead to a sustained slip. This can be shown to be unstable. This was the Geldart type A particle example that I gave before. Clustering can happen more naively because of cohesive forces. If you have wet particles, they can form little liquid bridges between one another, and that will force them to stick together. There can be electrostatic forces between the particles, forcing them to clump together. There's a lot of work that remains to be done on cohesion forces on particles. This is really just at the very beginning of its understanding, this problem. And even without that, If I have no flow whatsoever, if I just distribute particles, give them a random velocity initially, and allow them to collide in a way that's non-elastic, you can show that this simple problem, just a bunch of particles randomly moving around, colliding with one another, but every time they collide, they dissipate some energy. This process will lead to non-uniformity and clustering. That's called homogeneous cooling. Cooling, in a sense, you can think of this as a high temperature gas. You look at the molecules as they cool themselves down, except here we're working with particles. So of agitated so this is an unstable flow that leads to this, and here this is inelastic collisions. Okay. I just want to kind of wrap up and summarize by just showing this last graph, because I'm already going over my time here. This is a very naive graph, but it kind of summarizes what we've talked about before. We talked about the difference between dense and dilute two-phase flows, the limit being reasonably set at a volume fraction of 10 to minus 3. Above that, the interparticle spacing is not that large compared to the particle diameter. Collision should happen. There's a lot more that could be said on that question. Below that, you could assume that the particles don't see one another. And then there's the other question of whether the particles influence the fluid phase or not. This is what we would call a one-way coupled, the one-way coupled range. So if you assume that you have solid particles in fluid, there's typically going to be a density ratio of on the order of 1,000. It could be 2,000, 3,000 if you're looking at, if you're looking at sand or glass, it would be 2,000 or 3,000 kilogram per meter cubed. If you're looking at solid metals, copper, things like that, it could be 5, 6, 10,000, 6,000 kilogram per meter cubed. So it is reasonable to assume that we have about a factor of 1,000 in the volume fraction limit if we want to have a negligible mass loading. So if you assume, if you have a negligible mass loading, essentially the momentum conservation equations will not see the particle phase, and therefore we can safely ignore their influence. Otherwise, will have to be two-way coupled, meaning the fluid sees the influence of the particles. All right, I can share with Dr. Day the rest of the notes if you want. I didn't have much more on this question, so we'll essentially stop here. If you have questions, I'm happy to take them, and if not, I'll see you at 2 p.m., where we will make use of some of those concepts, but specifically we'll spend the first hour going through putting together a set of equations that we can solve in a purely Eulerian frame. Since last time we did a pure Lagrangian solution, this time we're going to do a Eulerian solution. All right, thank you for your attention.